Okay, I think we'll get started. Today we're just going to introduce the idea of energy and also the concept of work. So energy actually is a fairly difficult thing to describe because it's so fundamental. It'd be like describing what a number is without being able to point to your finger number one. We can kind of very loosely think of this as the stuff that allows us to do things. And so we came across the concept of energy because we're exploring our universe and getting things to work, and we needed this concept of energy. It is a fundamental aspect of nature and an important driver of physics. And in fact, we are learning physics via Newton's laws, F equals ma. But if you were to take some physics courses later on down the line, you'll actually cast physics in terms of energy, and you'll learn something called Hamiltonian mechanics, where energy is the principal driver. And it turns out that because energy has a conservation law, as we've talked about a couple of times through this course via Nodier's theorem, it has a symmetry, and that's a deep symmetry of nature between energy and time invariance of physics. Okay, so what are some of the properties? Well, there's no absolute zero of energy. We don't say this has zero energy. Oftentimes you'll see that, but it's always relative to something else. So the only thing that is physically relevant are energy differences. Energy is conserved, as I just mentioned. So this is going to be a key deep fundamental aspect of nature, but it also is just a very important thing that'll help us solve a lot of the problems that earlier were pretty difficult. Now will be solved almost trivially by using conservation of energy. Two main categories that we will break our energy down into, and that is kinetic energy. Our book uses the symbol K. Sometimes often out there you'll use the symbol T. This is energy due to motion. So it's only due to the motion of an object. Potential energy, on the other hand, is energy due to position of the object in some kind of situation. So this pen has a certain amount of potential energy because it's in the gravitational field of the Earth. Okay, so kinetic energy will be a quick one because it's always going to be the same. If we have one object, if we have more than one object, then there'd be multiple terms like this, m1, m2, m3. But it's simply 1/2 mv squared. So this is really the speed. It's not a vector, it's a scalar quantity. So it's 1/2 of the speed squared. Now, potential energy, though, that will be different depending on the situation. So I mentioned this pen in its gravitational field. We could have, like if I had a balloon, rubbed it on my head and stuck it to the wall, there'd be some electrostatic potential energy that the balloon is feeling. Springs, and so on. So we're going to cover springs and gravity here in Physics 1, then electric potential in Physics 2, and also at the very end of Physics 2, we will talk a little bit about Einstein's theory of relativity, and that theory shows that mass itself is a form of energy. Then finally, there's chemical energy. This will be covered in a chemistry course, but it's energy stored in the chemical bonds because the atoms are positioned relative to one another. So it doesn't feel like it might be energy due to the position, likewise for mass, but it's due to their position relative to one another. Okay, so because of this conservation, we'll talk much more about this. We can start with a ball up on top of a building. That will have a certain potential energy, and what it really is representing is the potential energy difference between some ground and some zero. So we could call this 0 and then this some potential energy U. But we certainly could have called this 0 and this minus U, or anything we would like. So it's really this gap that's important. And when this falls, during the fall, the potential energy starts to lessen because we are getting closer to the position of being on the ground, so our potential energy lessens. But we also speed up. We know that if we drop something, it will accelerate, so it's constantly speeding up. So therefore, it's picking up more velocity, and its kinetic energy is going up. And the key idea that energy is conserved is that every bit of potential energy that is lost during the fall turns into kinetic energy during that fall as well. And so during this fall, a change in potential energy will be exactly opposite the change in kinetic energy and vice versa. So if we drop a certain amount of energy, then we will gain that energy in kinetic energy. The units of energy, SI units, is the joule. And this is kilogram meter squared per second squared. How can we remember that? Let's go back and remember the kinetic energy formula. And this is one that'll stick in your head all the time, it seems. This is mass, so kilograms, and then this is meters per second squared, so it'd be meter squared per second squared. That's the unit of energy. Okay, let's talk now about work. Work is a form of energy. It's a little different. It's not a category like this, potential or kinetic, but it's another way we can talk about energy. We'll talk about energy in the form of work or heat energy lost or gained. So let's look at this work, and notice here we're going to use a W, which is weight before, but this is work, is force over a distance. So the force that it's exerted to move an object through a distance. So if we were to take a ball and try to lift it up to this height, we would need to supply a force equal to the weight. So we would need to supply mg of force. And so the work moving up would be mgh. That would be the amount of work done. Notice, this is important, any extra force, right, would accelerate that mass up, but we would not get more work if we accelerate it, because we also have to decelerate it to set it on top. So it really is the minimal amount of force needed to move that ball up. So any extra force doesn't result in extra work. All right, if we were to take the ball and set it down, so we put it up and then we take it and set it down, we'll do work, but we'll do exactly negative work. Right? And this is a little bit counterintuitive too. If you had a heavy rock or a bucket and you had to put it up on a big table and then you took it and put it down, it would sure feel like you did some work after that. And from a macroscopic physics of that bucket, you didn't do any work. But of course, physiologically, inside your body, your muscles are firing, moving ions across barriers. That's all molecular level work that's happening. So you are doing a ton of work when you do that, lifting that heavy object up and then carefully bringing it back down. But from the perspective of the object, which is what we'll be focused on here, no work is done. mgh up minus mgh down. Let's look at another example. Let's say we had this ramp, and on one path, we'll call that path 2, we just lift it up. Whoop, this should be mgy here. On one path, we lift it up, and that's just like lifting it up here. So the height here is y, so we've got mg times y. Now along here, we're going to push, or we're going to just imagine there's no friction here. We're just going to slide that up this ramp. Well, we have to, and again here, I didn't use W for weight, I just wrote it out. The weight of the ramp then is mg sine theta, and in this case, the way I've drawn the ramp, it would be minus mg sine theta. Well, let's look at our trigonometry. Sine theta, that's going to be y over h. So let's stick stick y over h into here. So we got the work for one is mg sine theta h. Okay, let's stick that into here. And so we're going to get mg y over h. The h will cancel, and we'll get mgy. And so, again, the energy due to position. We started on the ground, we finished at the top. It does not matter how we got there. In both cases, we end up with the same amount of energy difference, and in this case, the same amount of work. Now, where this would become important is if this was not frictionless, if we were sliding that up, we would have to fight the weight and friction, in which case it will require more work to slide it up the ramp than to simply lift it up the ramp. So we have to be a little bit careful here. The potential energy change is the same, but the work depends on the force that you've had to overcome. And in a frictionless case, that is going to be equal to the energy. So it's tempting to think of work as equal to the potential energy. And we will see, we haven't seen the formulas for this, but we will see that the formula for potential energy is mgh as well. So it is if we don't have other things involved like friction. If we do have friction, let's imagine pushing this box along the floor. If I'm here, I push the box over here, right? The box has not moved up. Its potential energy has zero change. So there's no change in potential energy, but I needed to push with a certain amount of force to move that box across. If it was on ice, it would just slide freely and I have done no work. If it's got a lot of friction, I would need a lot of work. And so the work will be just the frictional force times how far I move the box. Okay? So, moral of the story here is that work is a form of energy. It is not, though, potential or kinetic energy. It's a different way of kind of thinking about how work is distributed. So we'll see work, and then we'll also learn a little bit about heat, which is another way energy is distributed. All right, so over this lecture, the next couple of lectures, we'll talk about how to use energy to do calculations. We'll learn that some of the difficult calculations from the start of the course will actually be quite easy. And then we'll talk about because of the consequences of conservation of energy.